Hello everyone. Hello everyone. My name is Abhishek Bansal. In this video, I am going to discuss the mathematical operation of the boost converter. This is a boost converter. We have an inductor in series with the input source. Here we have a switch, single pole, single throw, and here we have a diode, and here we have a capacitor. Excuse me. So the boost converter, basically I am going to discuss again here DC to DC converter. I am not going to talk on the AC to DC because it would be similar to the rectifier. So we have a DC input and a DC output. The output is greater than the input. That means the VO is greater than V input. So here we can see that we are having an inductor. It is in series with the input voltage. Okay, and when the switch is on, that means this switch is on, so we can close the switch and this will become reverse biased. That means it's going to be an open. So when for the T on time, when the switch is on, the input source is going to feed what? It's going to feed the inductor. Okay, it's going to provide energy to the inductor, which is going to store it, and during this T on time, the inductor current is going to rise. Okay, again the input voltage applied to the inductor in the forward direction, and the current is going to rise from IL1 to IL2. Okay, this it is going to rise it. So now the circuit is open. The output gets its power from this capacitor. So this capacitor has to be large enough so that it supply the load current for the complete time duration. When I am going to close the switch, or for the time duration the switch is on for the T on period. Now when the switch is off, when the switch is off or the switch is open, the diode gets forward biased and there would be energy that is going to be stored in the inductor. Also the input source is connected, so both these are going to feed the load. Again I am taking load here for simplicity, resistive load. I am neither taking RL, I am also neither taking RLC, not even RC. We are taking the simple load to be a resistive load, and this diode, so the current is going to flow through the diode only. The inductor current is going to flow through diode, and the difference of the voltages between the input and an output, we can very easily say the input and output. I would be coming during the derivation, just after 1 minute. So this during the T of time, the inductor current is going to linearly decrease with the same slope, differences of the input and the output voltages. Okay, so again I am going to firstly discuss here the continuous conduction mode, and as in the buck converter there were some assumptions were made. Excuse me. The assumptions are valid for this boost converter also. That means I am talking of a periodic current. The inductor current is periodic and is continuous. The steady state operations still exist. That means the steady state, we are following the circuit, following the steady state conditions. The switching time is again T. The switch is on for a time period dt. The switch is closed for a time period 1 minus dt. Same as in buck converter. Okay. The capacitor is again has to be very large, because during the T on time it's going to provide the load supply current, and also it has to keep the output voltage at constant. And the most importantly, while doing the mathematical here, I'm assuming all the components are ideal. I'm not taking any of the non-linearities. I'm not taking the components are non-ideal. So let's take the t on time. So when the switch is on, we are having a switch is on. We are having a input source here, DC input source. I can say plus minus here VDC. We are having an inductor here. We are having a switch here. It's going to close this thing, and this diode is open, and we are having this. So the load is connected here. The load is connected here. This is a resistive load. So during the when the switch is on, if I just going to use the Kirchhoff's law, it's very simple because the voltage across the inductor would be simply what? The voltage, input voltage, and this will be L di by dt. And I can put this L here. That means the rate of change of current is equal to the V input by L. And by this slope is going to the inductor current is going to rise linearly. Okay. That means for an inductor, if I am going to talk on the voltage, this would be this is the close time, this is an open time, and this is again the close time. Now if I am going to take a inductor rise, I can say this is an I minimum. I can put at I maximum, and it's going to rise linearly, and this linear rise slope is what? V input by L. The slope here is V input by L. Okay, and we will see it's going during the t of time period what would be the slope during the t of time, and the difference between the maximum and the minimum, let's denoted by delta IL. Delta IL, which we can put, I would be putting excuse me, yeah, here also, like in the buck converter. So here we have taken a diode also, so there would be a current in the diode, and the diode current can be similarly referred, because the diode is off for it's a reverse bias, so it would be this line. During the t of time, when the is going to convert, when is going to convert from reverse bias to forward bias, this diode current is going to be will follow this thing. So let's come to and the capacitor is left. I would be covering shortly. So we got this would be, I can say, is equal to delta IL upon delta T upon delta T. We know the switch is on for a period of what? Dt. So this would be replaced by dt, or we can say delta IL is equal to V input by L into dt. This is for the t on period, or when the switch is on. Now when the switch is off, we are having the equivalent circuit would be what? We are having an inductor. This is an off, so we can remove it, and we are having this thing. Okay, and here we are having a load. Okay, we are having a V input source here. So when the switch is off, we can very easily see what would be the voltage across the inductor, and the voltage across the inductor is simply what? V input minus V output, and that's again going to be equal to LDI by dt, or I can take L here. We can say it's a V input minus V input minus V output upon L di by dt. That means this slope is now V input minus V output upon L. So it's going to decrease linearly with this slope. The rate of change of current or the inductor current is again a constant. Okay. So again in di, I am going to put it as delta IL. I am putting as delta IL, and this delta IL again delta t. We know this time duration is what? 1 minus dt. So this is the time duration for when the switch is off. So rearranging it, we get what? We get delta I L upon delta T equal to V input minus V output by L. Okay, and here this delta T is what? 1 minus dt, which we can take it here 1 minus d and then t. Okay, so this is the inductor current during the switch time period off, and for the steady state operation we know that the delta IL during an on and off would be equal to 0. So the steady state condition, we are putting the value of delta IL that we have derived during an on time and an off time. So the on time, it was what? V input dt upon L plus this thing V input minus V output upon L 1 minus d t. Okay, and this would be equal to what? 0. So L will go, this t will also go. We will have 0 is equal to V input d, and I am even expanding this 1 minus d here. We get V input minus V output minus V input d plus V output d. This V input d will get cancelled. We have now this 3 variables left here: V input, V output and the duty cycle, and we are going to get a relationship between the input and output voltage. We got V input minus V output plus V output d equal to 0, or we can say V input excuse me, V output taking common 1 minus d equal to 0, or this would be equal to this thing, and we can say V output upon V input is equal to 1 upon 1 minus d. This is the famous equation for input and output current for the boost converter during the continuous conduction mode. Okay, again the average inductor current has to be 0 for a periodic operation. That was the assumption we have made it, and that has only allowed us to simplify this equation. So now, if we see what would be an output power, we again are assuming the power conditions are ideal. That means we are not taking into account any of the losses. If I just simply take a power output power, the output power is going to be V square upon R, that is output, and is going to be input IOVO. Okay, and the input power is going to be equal to the input power. That means it's going to equal to what? V input I input is going to be equal to the V input and then I input. Okay, V input and then I input. So we are having a V input, I input is equal to this thing, and we can put the value of the V naught which we have derived. We can put the value of the V naught here also. We can put the value of, let's put the value of the V naught was what? It was V input upon 1 minus d, and this is going to be square upon R is equal to what? V input, I input. We can take R here, R would come here, okay, and we can solve for an average inductor current here. We know is going to be equal to an this is going to be equal to what? IL. This, if I just take this thing, this equation, yeah. If I am going to take the average inductor current is going to be what? V input upon 1 minus d the whole square R, and this is not a square, like here it's a square because it's basically a V input square, not R, but here it's a V input. So one input is cancelled. Okay. One input therefore gets cancelled. This is an IL. This is an average inductor current, and this is equal to VO IO upon V input. So now again we can get the maximum and minimum current. Similarly, like the buck converter, the I max is equal to IL plus delta IL upon 2, and the I minimum is IL plus delta IL upon 2. So again putting the value of an IL plus delta IL upon 2 for an I max. I am taking an I max. IL, I have just got it, it's V input upon 1 minus D square upon R plus, this is what? V input dt by 2 we already have and L. Okay, because I have already got it by di by dt. During the switch was on, this was the equation for delta IL that I put it here. Similarly, for that I minimum, it would be a minus sign here and it would be a minus. Okay, so that means the inductor current is always going to be positive and it's going to be continuous. Okay, and the condition that will make this minimum current to be positive only if the conductor is if the inductor current is continuous. Now similarly we can also get the boundary between the continuous and discontinuous inductor current. That means the I minimum has to be equal to 0, because otherwise it will fall below 0. Okay, and we will see that here the inductor current is going to be in this manner. It is going to rise, is going to down, discontinuous, going to rise, is going to down. Okay, here we have dt, here we have, I would be doing this during the discontinuous mode. Let me finish the boundary between the continuous and the discontinuous. So the I minimum I have said equal to 0, and the I minimum equal to 0. That means the I minimum was this, we have just made, so this would be equal to 0. Solving it, we can very easily say this is going to be equal to this thing, and we know T is what? 1 by F. So we can put F here, or we can say that V input and then V input will get cancelled. We have 1 upon 1 minus D the whole square R equal to 1 by twice LF. Rearranging it, I am going to get LF minimum equal to 1 minus D the whole square R upon 2, and this would D would be there. Okay, so this is the, again we have got the minimum. This should be the minimum inductance value and the minimum switching frequency, so that the converter continues to operate in the continuous mode instead of the boundary, avoiding the boundary condition. So from the, now we can okay, now I have missed one thing that was left was basically the capacitor. I am going to take again an output voltage ripple and the capacitor also, because the capacitor has to be large enough, and practically it would be large enough to an extent that it's going to have some finite value. So let's put the capacitor voltage, or the capacitor current. If I'm going to put the capacitor current voltage waveform is, these are straight lines, this is a slant line ramp down, and it's a, so this is a dt we know, this is a time serial, this is a t axis, we have, this is a capacitor current, and this would be what, minus V naught by R, because I have taken a resistive load, and this again, like in the buck converter, would be the change in the, this again change in the charge. So we can say that a finite capacitance is going to result in some fluctuation, and it's going to result in then fluctuation in then output voltage, or in simple form we are going to experience a ripple, and again I have to calculate a peak to peak output voltage ripple. Now I can very easily calculate the peak to peak ripple using this graph only, and we can say, if I just take the modulus of the delta Q, it would be CV naught, and here V knows, it would be equal to V naught by R dt, because this would be the, this is not a triangle now, it's a rectangle, so we can take delta Q into dt. So V naught by R into dt, that's what I have taken here, and that would be equal to delta Q. So we know the ripple is what, delta V naught, it is a ripple in the output voltage, and that would be equal to what, CV naught if I am going to use this expression, and delta Q if I am going to not just take these two equations. So we can say the delta, this has to be delta V naught, otherwise V naught will get cancelled. So this delta V naught is equal to what, V naught upon R dt upon R upon C. T we can replace it by frequency. Okay, and if I have to take a variation with respect to an output, I can put V naught here, and we get delta V naught upon V naught equal to D by RCF. That means the change in charge delta Q was this, and we have got the peak to peak voltage at the output as a fraction of the output voltage. Okay, so we have got an output voltage here, the peak to peak variation, and if we take C here, if I just rearrange it, I will get C is equal to D upon delta V naught upon V R and the switching frequency. So this much should be the minimum capacitance for this ripple voltage. Okay, and we know that the capacitance also have an equivalent series resistance ESR. So the peak to peak variation would be the capacitor would be same as the peak to peak as the maximum current of the inductor, or I can say delta V naught, the ripple, into an ESR equal to delta I, sorry, I would be here, I R C, let's put it by dash, and this would be equal to I max, IL max R C, because the peak to peak variation in the capacitor current, it's the peak to peak variation in the ripple voltage, it's a in the capacitor current, the peak to peak is equal to the maximum current in the inductor. So the voltage ripple due to ESR would be this, and with respect to an output voltage it would be this. So this was the continuous mode. Let's take the inductor resistance also, because inductor should have small resistance, otherwise it's going to cause power loss, high power loss, and by choosing the small resistance we will also going to obtain an higher efficiency. Excuse me. Yeah. So let's not take a discontinuous mode, and I would be closing then this boost converter. The boost converter, we have already mentioned that it's not that we cannot operate into discontinuous. We should always operate in the continuous mode. Sometimes it's desirable due to the nature of the application that we have to choose the discontinuous mode of operation. Again, we are going to take that the average inductor voltage is 0 and the average current in the diode would be the same as the load current. So in the discontinuous mode, we are having an IL here. This is line is an IL, and this is basically an Imax. This is the rising down, discontinuous rising down. Okay, sorry, I have to draw the same peak. I have not drawn the same peak here. So this is a T, this is a DT, this would be D1T. Okay, and again the difference of this to this is what delta IL. The inductor voltage was definitely it was like this way in the continuous mode, but here again it would be this. So this was a similar graph. If you would see in the buck converter also, I have done the same thing only. Okay, and this was the DT, this would be D1T, and this is a T. So this is what this peak is what V input minus V output. Okay, V input minus V output. And if I have to take a diode current, because the diode initially was reverse biased, during the T on time it's a reverse bias, it rises down, it's a discontinuous, so rises down. Okay, so it's periodic here, and this one is what D1T. The peak is Imax here again. The peak is Imax. Yes. So this is a diode current, and the inductor and the diode currents, you can see there is a discontinuity here. So the voltage across When the switch is on, the voltage across the inductor is input only, and when the switch is off, the inductor current is positive, but the inductor voltage is what? V input minus V output. So the inductor current, we can see the inductor current is decreasing until it reaches 0, but it do not cross an x-axis or t-axis because of the presence of the diode. Okay, and when the switch is off, when the switch is on, the diode is off, and therefore the inductor current is 0, or we can say V input dt plus V input minus V output dt d1t is going to be equal to 0. It's exactly similar like a buck converter, and we are going to get V input d plus d1 upon d. Okay, so we can say an average diode current would be what? It would be average would be what? 1 by T Imax Imax d1 T. Now we are taking an average one, it would be also 1 by 2 here, and that would be equal to what? T will get cancelled, half Imax d1. Okay, so the current Imax is same as the change in the inductor current. This would be a delta IL here, and it would be what? Imax is what? Imax therefore would be delta IL, and we have already calculated delta IL was V input dt upon L. We can substitute the value. This is D. We can substitute the value of this into this expression. And we will get ID equal to half of the V input dt upon L into d1 equal to V naught R. We can equate the equation and solve for the d1, and we will find that d1 is equal to V output upon V input upon 2L upon 2L R dt upon R dt. So this would be the d1 expression for the, and we can again solve it into okay. So we can, if we are going to further solve it, so we have got a d1. Okay, we can put this d1 into our equation. V output equal to V input d plus d1 upon d1. That I have derived in the beginning of this discontinuous mode. This expression for an input and an output relation. Okay, this was because of V input dt plus V input minus V output. This was not dt, it was d1t. From this I have derived this thing. Now I can put the d1 here, and this d1 is going to result into what? A quadratic equation. We are going to solve it. Okay. So this quadratic equation, we have got it, and once you have got this quadratic equation, it would be like this: V input upon V output upon V input minus V output upon V input. We are getting a quadratic equation: V output upon V input minus d square RT upon twice L equal to 0. We can solve the quadratic equation, and after solving the quadratic equation, we will find that V input upon V output equal to half of 1 plus twice d square RT upon L. and this would be discriminant. This would be discriminant. Okay. So the boundary between the continuous and the discontinuous current, it occurs when, let me again just take the rewrite the equation. It would occur, we know that the V output equal to V input upon 1 minus D. So the boundary is going to occur when this D, when the D1 equal to 1 minus D. Okay, because here we have got the V input minus V output was what? V output was V input D plus D1 upon D1. So when this D1 is equal to 1 minus D, that means equal to 1 minus D, and this would be 1 minus D. So this D will cancel, and we were going to get back again our continuous conduction mode. So that's why we can say very easily the boundary between the continuous and the discontinuous current going to occur when the D1 is going to equal to 1 by 1 minus D, and again the like in the buck converter, I minimum equal to 0. Okay. Thank you.